looking at two gas laws. The first one is Dalton's Law. Definition of Dalton's Law is the total pressure closed system is equal to the sum of the partial pressures. And we find that by taking the total pressure of the system by each individual gas added together. So here's a problem. Calculate the partial pressures of 12.350 liters of chlorine, 14.220 liters of oxygen, 13.430 liters of nitrogen. The closed vessel total pressure is 112.98 kilopascals. Now we're going to take a slightly different equation to do this. The pressure of the gas we're looking for is going to be the volume of that gas, the total volume, multiplied by the total pressure. Now, if you look back at the equation, we take individual gases. We need to find what percentage that gas is in the total. So we're going to use volume here to find that percentage. So we have chlorine, oxygen, and nitrogen. We sum them up, and we get 40.000 liters. So to find the pressure of chlorine, we take the volume of chlorine divided by total volume, multiply by the total pressure. So we have 12.350 liters as my volume of chlorine, divided by 40.000 liters, multiplied by total pressure, and we get pressure of chlorine of 34.883 kilopascals of chlorine. Now, I did ask for the pressures for all three, so I'll need to find the other two. So if I take my 14.220 divided by 40 multiplied by 12.98, take my 13.430 divided by 40 times 112.98, we're going to get 40.164 kilopascals and 37.993 kilopascals. These are actually my answers. This is done with a problem here for what I'm asking. But there's a check to make sure we do this right. If I add them all together, I get 112.98, which is my total pressure, which is what we should have. Here's a problem we'll do in class. Determine the partial pressures of carbon dioxide collected over water at 26 degrees. The barometric pressure is 115.9 millimeters of mercury. All right, great. So let's look at second gas law. Second law is Graham's Law. Graham's Law has to do with something called diffusion. Now, diffusion state is the process of going from a region of high concentration to low concentration. And I've got to stop this because I don't. All right, so Graham's Law is expressed in the equation that the rate of the individual gas is equal to the square root of the density of the second gas divided by the density of the first gas. So it's the inverse square root of the densities. So here's a look at a problem. Determine the rate of reaction of a gas with a density of 1.244 grams per liter as opposed to a gas with a density of 2.003 grams per liter. So we want to find the rates of reaction. So we take our second gas, 2.003 grams per liter, and divide it by my first gas, 1.244 grams per liter. Grams per liters cross out, and I'm going to get 1.269. That doesn't tell me much. So we have to have an understanding. If my rate is greater than 1, then the reaction is faster. If my rate comparison is less than 1, then it's slower. So what we're going to say here is for this reaction, gas 1 is 1.269 times faster than oxygen, and I'm going to have to bring this up so you can see it. That's my answer, that gas 1 is 1.269 times faster than gas 2. All right, so look at the second problem. Identify the rate of diffusion of oxygen to fluorine. In order to do this, we do have to do a slight derivation. So here is my equation again for Graham's Law, and I can take the densities of grams per liter for both densities. Now, using molar volumes, 22.4 liters per mole over 22.4 milliliters per mole, that's one. I'm not changing the values at all. My liters cross out, my 22.4s, I'm left with grams per mole. Grams per mole is unimolecular weight. So it's also equal to the square root of molecular weight of 2, molecular weight of 1. We'll do this one in class. All right, so copy these two down. We'll do them as well afterwards. Hopefully this wasn't too bad. Take care. Be good. Bye.